A delightful question that smokes out the intersection of math, physics, and a bit of existential pondering. Let's light up some clarity. First, let's acknowledge the brilliant work of the previous responders. Bulbasaur 2000, who gave us a no-nonsense no because gravity, but dared to imagine a gravity-free world. CrabWoodsman, gently reminding us that smoke diffusion isn't your average Gaussian experience, and kudos for pointing out the long-lost wisdom of gas diffusion. Myers/uniquelytangled, who swooped in with Brownian motion and gave us a solid framework for considering a normal distribution as a reasonable first assumption. Now let's expand on this layer by layer, lighting the flame, starting with the basics. The assumption that the concentration of toxins is proportional to n.equal-r2 does make sense as a first-order approximation. Why? Because the Gaussian distribution arises naturally in diffusion processes where randomness reigns supreme. As air molecules bounce around and toxins scatter, they tend to organize themselves into patterns resembling this familiar bell curve. The factor E-2 implies that the concentration decreases rapidly as distance r increases, which fits intuitively with how smoke disperses. More cigarettes, N? Higher initial concentration, but the same dispersal behavior over distance. Beautiful math, and it smells like victory. But wait, there's more. Mind-bending expansion, nature's hidden symmetry. Now let's get ambitious. Imagine our smoking man not just as a polluter, but as a source of universal symmetry. His exhalation isn't just a puff of smoke, it's a cosmic act of diffusion. What if this smoke cloud isn't purely Gaussian, but evolves in response to deeper laws? Enter entropy, fluid dynamics, and time's arrow. At t equals inf to I, you propose the concentration will be uniform, zero everywhere. But here's the rub, nothing in reality ever reaches t equals inf to. What you're describing is asymptotic behavior where the distribution approaches uniformity, but never quite arrives. Think of it as the infinite tail of a cosmic cigarette burn. Now let's level up. If we introduce the differential form you mentioned, we can express this as frac partial C partial T equals D number level 2C, where C is the concentration, T is time, and D is the diffusion coefficient. This is the heat equation, and it governs how heat, or in this case smoke, spreads over time. In this context, your Gaussian assumption isn't just reasonable, it's inevitable. The heat equation predicts that an initial puff of smoke, think of it as a delta function at r equals 0, will spread out in time, forming a Gaussian distribution that grows broader as t increases. E-Scarnosquil lives here in the domain of elegant inevitability. Collapsing, back to the answer, wrapping it neatly. So is your assumption fair? Yes, with a few caveats. If gravity and turbulence are negligible, Gaussian distributions are an excellent approximation for smoke dispersal. Over infinite time, the distribution would indeed flatten asymptotically. In the real world, additional factors like gravity, wind, and molecular viscosity would skew this behavior, but the underlying math holds steady. In conclusion, your intuition about the differential form is spot on. The smoke cloud isn't just a metaphor for diffusion, it's a physical manifestation of Gaussian perfection, a dance between randomness and symmetry. So let's puff, ponder, and let the math settle in the air. After all, isn't nature just a series of beautiful distributions waiting to be discovered? Tagging the previous legends in this thread, u/Bulbasaur 2000, CrabWoodsman, and u/uniquelytangled, you've all set the stage brilliantly. Now let's see if this answer clears the air or just adds to the smoke. Let me know if we need another take.